All right, welcome to day 20 from last year's Advent of Code. I'll bring up the problem description here so we can see what's going on. This problem, I consider it to be easier than the preceding days for the most part because there wasn't anything too challenging from a performance perspective, but it's very intricate. There's a lot of ways to mess this up with off by one errors and that sort of thing. So you have to be very, very careful. We get a list of numbers and then we have to mix them. So basically what happens is the numbers are all going to get moved. Each individual number is going to get moved. And it's going to get moved based on what it is. So we have these numbers. We can imagine they have indices basically 0 through whatever the list is. And we start by moving 1. Because 1 is a positive number, we move it to the right and it takes 2's place. So it moves 1 over and takes the place of 2. Next, we have to move 2. 2 is the next number we were going to move, and it's a 2, so we move it 2 places over. So 2 goes. So here we have 2, 1, negative 3, and it becomes 1, negative 3, 2. The next number we have to move is negative 3. Now, negative 3 is negative, so we move it left, and we move it left 3 spaces. So we go past the 1, and then it wraps all the way around, and it comes over here. It moves in front of the 1, it moves in front of the 4, and then moves in front of the 0. So this is its final resting place. Now we have to, keep moving the ones that are sort of next in line. So we already moved the 1, we already moved the 2, now we move this 3. It moves to the right, ends up here, and so on and so forth. So there's a lot of things to keep track of. Once we have moved everything in part 1, so we need to look for the 1,000th, 2,000, and 3,000 number after 0, wrapping around, doing modulo, and I think then we add these numbers together. So we do the mixing process once, and we add them together. Then what happens in part 2? And part 2 gets a little crazy. First, we have to multiply every number by a decryption key, very large number. I forget, let's count. 1,000, so it's 800 million something. So that's the first part, is now instead of moving things by spaces like 1 space or 3 space or 2 spaces, now we're moving them a lot. We have to be very accurate with how we're doing the modulus operation here. And then we also have to mix the list 10 times. And the really tricky part is that we have to move the numbers in the same order each time. So in this first part, we moved 1, and by the end of the day, 1 was back in the first position, but we moved, say, this 2, also ended up in the same position. These numbers didn't actually move as much. So we have the 4. The 4 starts at the end of the list here, and by the end of the mixing process, it's in the middle. On the second time through, just imagining we keep these exact same numbers, this 4 still moves last. So we still move the 1 first, the 2 second, the negative 3, and then we have to move the positive 3, then we move the negative 2, then we move the 0, then we move the 4. So even though they're all mixed up, we still have to keep moving them in the same order. So we have to associate the indices with the numbers as we move them around. All of this is actually made a lot easier in Haskell by the fact that we have the sequence data structure, and the sequence data structure allows us to insert, delete, and just access arbitrary indices in logarithmic time. Super helpful. I'm not sure you get a data structure like that just out of the box in most languages. At least it's not one of the most common libraries you'll use. So really helpful that just the standard queue we have in Haskell just allows that kind of indexing. Okay, parsing, no big deal. Bunch of, signed integers. Okay, nothing hard about that. So let's go to the easy part. So the easy part, we're doing kind of it's like a state evolution, although it's also kind of like a fold. It's actually neither of the. Well, it's a state evolution in the sense that we're just doing raw recursion. We're not folding with an accumulated value. We're just keeping track of this. I guess it is an accumulated value, but either way you want to look at it. So what's our initial state given our list of integers? We make a sequence out of these, and then we also make a separate list containing the indices. So we'll see how this matters. So each step of the way, we are going to modify the sequence by moving one of the numbers around, and then we will then change the queue of indices that we have to deal with. So once we're out of indices to move, that's our base case, we just return the queue in its state. Now, assuming we have our next index to move, okay, so we get the value at that index, at that index within our queue. Now we delete the value at that index, and now we calculate its new index. How do we do this? We take its previous index, and we add the value itself, and then we take the modulo of the queue by modulo with its length. So then we insert the value at the new index, and now here's the tricky part. We actually have to change some of the indices. So every index that was less than the new index has to change because it has to subtract 1. And I think this makes the most sense if I go here. Let's imagine, so our indices look like 0, 1, 2, 3, 4, 5, 6. After we moved the 1, what does that change to? The 2 now occupies index 0, so the indices list is now 0, 2, 3, 4, 5, 6. When the 2 moves over here, the indices list is now 1, because the negative 3 has moved here. 1, 3, 4, 5, 6, and so on. So the smaller ones all have to subtract by 1. But then we just make our recursive call, so our queue has been updated, and then we just add the unchanged to the end of the ones that we did change, and we just make a simple recursive call. It's kind of intricate, but it's not a ton of code for part 1. For part 2, things get a little bit more challenging. So here we do need to do a state evolution in the sense that we need to do 10 different mixing steps. So we have this kind of boilerplate that I like to use. So once that count reaches 0, we just return our queue. And now, assuming it's not 0, we have to look at our indices, and we have to call hardtail. And hardtail ends up being the primary function that is doing all of this. This gives us our new values, and then we have to recalculate the indices. So that's exciting. We'll get there when we get there. We're going to have this recursive step with n-1, but first let's look at what we're doing in hard. Hardtail, the mixing step in hard, is mostly the same. We still deleted the index. We get the value, etc. Insert. What's changing, though, is that instead of it just being a sequence of the integers, it's a sequence of the integers and their previous index. So, or I shouldn't say its previous index. We're keeping track of its ordering value. So we want, for example, we want this 1 to be permanently associated with sort of the order value 0 or the order value 1. I forget which way I did it, but we can see this in our initial construction. We take indices 0 through the length, and we zip these together. We multiply all the numbers by our key, but we still zip with the indices. And so that's our tuples. So each number is always associated with its ordering. So what is our our queue is modified. We deleted the index. We get the we modify the values so that we can get its next index, because we have all these rules with a decryption key. We eventually insert the val with the order at the new index. Say next index plus value on the length of the queue. And now we have to do adjust indices. So adjust indices, it's similar in concept to what we did up here with this i-1, but it's more complicated. So basically, if I have to think this through, so we have our new index and our old index. Next index is actually the old index. That's the name is a little misleading. But we have different behavior based on the relative position of old and new. So if the old index is greater than the new index, so if we shifted this element left in the list, then, well, what happens? We have this lambda function over the rest of the indices. Now, if n of I is greater than the new and I is less than the old, then we return I plus 1, else I. So there's a certain segment of indices in this that are between old and new. And those ones need to be incremented in this case. If we moved it left, some indices need to be incremented. If we moved it right, so if old is less than new, we need to decrement some of them. So the fact that things are just a lot more fluid here because we're not just doing a single mixing step, that's what really necessitates the fact that sometimes we have to add indices, sometimes we have to subtract them. But if we move to the same space, there's no difference. That's a nice little base case there. So the adjustment is a little more complicated in this step. Now the last thing we need to do is get our list of indices, and this actually isn't too terrible. I needed to write a sequence to list function. Apparently this doesn't exist in the library, which is a little weird. But anyways, let's focus back on this. So how do we get the new list of indices? We want to take our final sequence from one mixing step and derive the ordering of indices to use. So how do we do that? We take sequence.zip with our inputs and just everything in order as it was. Now we need to sort by that order. So sequence.sort on, and we're doing second.second on this zipped item. So what exactly is second.second calculating? So as we're looking at this, the first values, remember our inputs, this is the final mixed up set. And this consists of tuples. So we have the value itself and we have its ordering. So we ultimately want to sort based on this ordering. We don't want to sort based on the value. We also don't want to sort, I guess, based on the 0 through n. But what happens? We sort on the ordering itself, but then the first part of the tuple now contains, I guess, its new index. And so this gives us, okay, the list of the indices that will go through them in this new mixed up set. And so we get another sequence to list based on the first item, if we sort it by order. So we're sorting it by this guy, but we are eventually returning these guys. So that's the step that happens here. We get the new indices based on the new set, and so we substitute a new set with next indices. And then, solve it. We do 10 runs of this, and we find the index of 0, and we just, do all this logic, 1,000, 2,000, 3,000, beyond that value. And we take a sum of those, and we get our answer. So very intricate problem, but not as challenging from a performance perspective if you use the sequence data structure in Haskell, which is really nice. So hopefully you enjoyed that. I'll be back next week, hopefully with the next couple of videos. Almost getting to the end here. I'm almost done. So if you're enjoying this, subscribe to our YouTube channel and make sure to subscribe to the Monday Morning Haskell mailing list. That link is in the video description. So thank you so much for watching.